Ravikumar will talk about the Expxorcist.
Thanks to the organizers and thanks to the audience for being here as well. So I'm going to talk about the Exorcist. Exorcist is a bit difficult to say, so just call it Exorcist. So it's about non-parametric density estimation. So this is a problem where you're given n IID samples, x1 to xn, drawn from some distribution with density f. And the goal is to recover this density f from these n samples. And we are in the non-parametric setting, so we want to do this by making as limited assumptions on the function space script f as possible. And so this is one of the big open problems. And so this has also attracted a lot of attention in deep learning community and deep learning approaches, where there have been some limited successes for some data types, like some specific classes of images. But this is still an open problem that many want to tackle. But of course, this is also a very, very classical problem. And here is a very simple approach that all of us have used, which is kernel density estimation. That works very well and is in some sense also optimal for various settings. And so this is a problem where this is an approach where I have a bump distribution over all of my n samples, and then I just have a uniform mixture over all these bump distributions. And so these bump distributions are specified by the kernel. So very simple, available to us in closed form, and this is also not only consistent but also minimax optimal for a whole bunch of function classes. So here is one such function class, so Sobolev, order 2. So here I'm in the one-dimensional case, so I just have a single scalar random variable, and if I look at the class of densities, where if I take the double derivative, its L2 norm is bounded, and what I want to focus on is this risk, which is mean integrated squared error. So if I have an estimator f hat n, look at its integrated squared error, and then you take an expectation because this guy depends on the n samples. And so if I look at this guy, the minimax rate for this over this function class is n to the minus 4 by 5. Right? So this is again a very classical result in that our students see in one of the earliest classes. And this is achieved by kernel density estimation. So this is the best possible rate for this function class, and it is achieved by kernel density estimation. So what's the problem, right? So what is the open question? So that was for 1D. As we move to higher dimensional settings, say let's say d dimensions, so x1 through xn are in r to the d now, okay, so where d is larger than 1. And so for this setting, again if I focus on the mean integrated squared error, now the minimax rate is n to the minus 4 divided by 4 plus d. Okay, so this is the minimax rate, and this is also achieved by kernel density estimation. And so what is the problem here? The problem is that if I look at sample complexity, which is the number of samples I need so that this risk is bounded by epsilon, this now, just by bounding this by epsilon, I essentially get that the number of samples have to scale exponentially in 1 over epsilon, right? Exponential as a function of d, the dimension. And this is very, very large even in our big data era, right? So there are always these numbers more than the number of atoms in the universe and so on, so you quickly get into those territories, right? So we do not have these many samples so that I can get the risk to be less than epsilon, okay? And so this is for a very, very simple function class, though you may also argue it's too flexible, right? So these are the so-called smooth functions, but it's still, for most infinite dimensional function classes, you essentially face this exponential sample complexity problem, right? The number of samples that you need scales exponentially in the number of dimensions, and this is not possible in the big data era, even in the big data era, right? So what do we do? So even in the high dimensional parametric settings, where my model parameters lie in a finite dimensional space, but it's very high dimensional, not infinite dimensional, even there I have to impose some assumptions on the space in which the model parameters lie. And similarly here, given this exponential sample complexity, the real question then becomes, what assumptions am I going to impose on this function space, on the density, right? And so one quick note is that instead of imposing my assumptions on f, the density f, I can impose my assumptions on the logistic transform of that density. The reason is that no matter what assumptions I impose on eta x, because this is a logistic transform, f will always be non-negative and normalized to 1. So I need not worry about those two constraints at the very least. Okay? So in the rest of the talk, and in fact this is what many have also done dating back to Silverman, which is that people impose the structural assumptions on eta rather than f. Okay? So that I at least don't need to worry about positivity and normalizability. But again, I haven't really done resolve the exponential sample complexity issue. Right? So now what I want to think about is what assumptions can I impose in the logistic transform of the density. And so one very natural assumption is to impose some kind of smoothness assumption, and one canonical smoothness assumption is that it lies in some reproducing kernel Hilbert space. And so this again dates back to Silverman and with some other follow-on work in the 90s and even in 2000s. The issue is that this still has exponential sample complexity because this is still a very large function space, a set of all smooth functions where the smoothness is defined with respect to some kernel function. So this is still a very flexible function class, so still exponential sample complexity. But we also lose something that the kernel density estimation had, which was the simplicity, computational simplicity. Now, in addition to the sample complexity bottleneck, you also have a computational complexity bottleneck, which is that, so here my assumption is this eta lies in an RKHS, and now I actually have to estimate this from data, right? So that's my problem. So I typically have some goodness of fit measure which says, okay, how well does this eta fit to the data, and the constraint that this eta lies in this function space, right? And so this is typically an infinite dimensional optimization problem, which is hard. So there are computational issues, and the typical way in which people solve this infinite dimensional optimization problem is that they use a finite dimensional approximation to the function space. Now, in many or in most RKHS settings, this is not really an approximation. You have something known as a representative theorem, where you have some finite dimensional representation given the samples which you can solve, but in many of these settings the representative theorem does not hold. So the finite dimensional approximation to the infinite dimensional function space is an actual approximation. So many of the statistical guarantees, even this exponential sample complexity, I can't really say given this finite dimensional approximation. Okay, so that's where we are. In some sense, we are worse off than the kernel density estimation. Right? Empirically, this might be preferable to kernel density estimation, but still, in terms of guarantees, we are worse off. Okay, and so people said, okay, let's try to impose some more stringent assumptions, because clearly we have to impose some more stringent assumptions. And one such assumption is structural, which is an ANOVA type decomposition of my logistic transform. So eta now factors into some node-wise functions and pairwise functions and higher order factors. Okay, and where I essentially assume that each of these guys lie in some function space, set of smooth functions and so on. Right. So each of these in turn lie in some infinite dimensional spaces, but I again have the multivariate logistic density transform at least has some additive structure. Right. In many of these papers, the sample complexity analyses are unavailable, but I can imagine that if I roll these out sufficiently farther, then it's going to be exponential as well. And also, I'm still left with the computational bottlenecks, because again, I have an infinite dimensional optimization problem, and I have to make these finite dimensional approximations when all the statistical guarantees go out of the window. Right? And so this is where we are. And again, I want to emphasize the computational bottlenecks, even setting aside the sample complexity analyses, right? So again, like I mentioned, in many of these recent methods, even the exponential sample complexity analysis is not available, but even setting that aside, it's a computationally very difficult problem, right? And so I mentioned finite dimensional approximations to the infinite dimensional function class, function space, but there is one additional issue, which is that the goodness of fit measure of this eta x to the data typically involves the likelihood, and this likelihood involves a normalization term. Since I'm parameterizing this with respect to the logistic transform of the density, and so this typically involves this multi-dimensional integral, which is intractable. Okay, so typically I do not actually, the goodness of fit measure in turn, tractable versions of these at least, involve surrogate likelihoods rather than the likelihood itself. Okay, and so I essentially have this additional thing that I did not talk in detail about. And so there are these both statistical and computational bottlenecks in non-parametric density estimation, and that's why this is a big open problem. So now we come to Expxorcist, right? So this is really our structural assumption. It's very similar to the ANOVA type decomposition. So again, this should be plus dot dot dot, right? You can have as many higher order factors as you want, except that the higher order factors have this tensor decomposition where they are a product of node-wise functions. Okay, so this is our Expxorcist structural assumption. So why Expxorcist, right? So it's an homage to the anti-paranormal non-parametric methods like non-paranormal skeptic. So we thought, what's the next thing that can come up? Expxorcist, right? So, but we are calling it the Expxorcist because it also involves exponential family densities, which I'll just talk about shortly. So that's our class of non-parametric density estimation densities and as well as estimators. And so I want to emphasize that we have a computationally tractable estimator, right? So it scales to very large dimensions. So it's computationally tractable, and moreover, we finesse the exponential sample complexity. The sample complexity actually is as if you have a single dimension. Okay. If you look at this form of the density or the logistic transform of the density, so essentially it's parameterized by some univariate functions, right? So at least the hope would be that the sample complexity that I would face would just correspond to a univariate non-parametric regression, and that's essentially what we see. Okay, but this is still a multivariate density estimation, non-parametric multivariate density estimation that we are doing. Okay, so let me delve a little bit further into the form of our Expxorcist density. So this is again the overall form of our joint density. So inside the exponential, I have this ANOVA type decomposition. So, and again, like I mentioned, the higher order factors are given by this tensor decomposition. So I've also added these parameters, theta st, and so on, for each of these higher order terms. So overall, the set of parameters, if you will, correspond to some scalars, theta s, theta st, and so on, as well as these node-wise functions. Okay, and so that's why this is a non-parametric problem, because these are functions lying in some function spaces. So given this joint density, and again this is with respect to some base measure, where I'm assuming this is a product base measure that's given to us. If I look at the conditional density of one variable condition on the rest of the variables, okay, so if I focus on this conditional density, it looks like this. Okay, and this conditional density you can see that it's in an exponential family form, where the sufficient statistics are essentially this node-wise function. So here, if we focus on xs, then this is an exponential family with sufficient statistics b sub s, and so this is the parameter corresponding to the exponential family, right? And so this parameter is a linear combination of the sufficient statistics of the other variables. Okay, so that's the natural parameter. So it has an exponential family form, and so what we can show is that this is an if and only if. So given this joint density, very simple algebra can show that this is the conditional density, right? What we can show is that this is actually the unique joint density which gives rise to these conditional densities. Okay, that takes a little bit more work, but you can again show that. Okay, so there are other joint densities that are consistent with this set of conditional densities. Now, in general, just specifying conditional densities are dangerous, right? So even with two variables, if you independently specify x given y and y given x, these need not be consistent at all with any single joint density, right? They can be inconsistent with any possible joint distribution over x and y, right? So in other words, if I allow the conditional density of xs given everybody else, right, and so this is h is just the logistic transform of this conditional density with respect to this base measure. If I just specify these independently, so let's say this is h sub s, where I have specify these independently for each and every variable, these need not be consistent with the joint density, right? So you can show this even with two variables, and this can also be shown. This has also been investigated in various contexts. The interesting thing about our case is that we have an exponential family form. Okay, so what's the difference between the completely general case and an exponential family form case? It is that this logistic transform of this conditional density, which is again a function of my node variable and the rest of the variables, factors as a function of that variable and as an arbitrary function of the rest of the variables. Okay, it's just this minor structural assumption that this logistic transform of my conditional density factors this way. That's it. Okay, so this is the exponential family form. This is what I call the conditional density of exponential family form. Okay, just this factorization assumption. And what you can again show is that if my node conditional densities have an exponential family form, again what I mean by that is that the logistic transform factors into a function of that variable and an arbitrary function of the rest of the variables, and you have complete, if I just allow you complete freedom in specifying this, both this function as well as this function, and then I ask, is there a consistent joint density after all of you have specified your node conditional densities independently? We have a theorem that says that these can be consistent with the joint density if and only if this function of the rest of the variables actually has this form. If it does not have this form, it will be inconsistent. If it has this form, then it will be consistent, and there will be a unique joint density of our Expxorcist form. Okay. So even though we started off with this kind of slightly stringent seeming ANOVA decomposition, it actually follows from this very general non-parametric assumption, which is that the node conditional densities have exponential family form. And again, what I mean by that is that the logistic transform factorizes. That's it. That's the only assumption I'm making. Under that assumption, you can show that this is the only possible joint density that's consistent with this assumption. Okay, and so this is where we are. And so this is our Expxorcist density, and since it's naturally connected to this conditional densities of exponential family form, our estimation procedure is very natural, right? What I'm going to do is essentially estimate these conditional densities at each and every variable and then just stitch them together. Okay, and so that's really our estimator itself, which is I'm going to estimate these conditional densities again non-parametrically, because here these conditional densities involve these node-wise functions, right? bs, bt, and so on, and it also involves some parameters theta s, theta st, and I'm going to estimate these at each and every variable, right? And I also have some identifiability assumptions. The L2 norm of the node-wise functions is 1, they integrate to 0, and these just for sign-based identifiability, these node-wise parameters are non-negative. And so how do I do that? Again, I can just use an MLE based approach, and you can again show that this is just a node conditional log likelihood, and so this is essentially the goodness of fit term for measuring the goodness of fit of all these node-wise functions to the data, and then I just have this very simple node conditional MLE. Okay, so I have this, but this is still difficult computationally because this is still an infinite dimensional optimization problem, right? Because all of these guys lie in some function space, and which are potentially infinite dimensional, right? So what we do is essentially a truncated basis approach. So I'm going to assume that there is some orthonormal basis that specifies the function space for each of my node-wise functions, and then what I'm going to do, just for computational reasons, is just look at the truncated basis, right? Just take the top n basis functions, and then I have this error term rho, right? So in my statistical analysis, I have to take into account that I have this error term rho, right? But computationally, I can now, if I just work with this truncated basis, I now have a finite dimensional optimization problem, right? Where I'm just going to estimate the truncated basis coefficients, okay? And so I have this finite dimensional optimization problem. There is still one caveat, which is that this is still non-convex. Okay? Finite dimensional, I can still solve it using proximal gradient and get to, and we also use alternating minimization to get to some local minimum, but I can only guarantee that I can get to a local minimum rather than a global minimum. Okay, so that's one minor caveat, but we still analyze our local minima rather than some global minimum that is difficult to get. Okay, so this is our result, which is that it's actually based on which uses some of the techniques from Montanari and May's recent paper, which is looking at the landscape of the population log likelihood. What we can show is that the if you look at the Expxorcist MLE with the truncated basis expansion in the previous slide, and let's say the estimate is alpha hat m, what you can show is that any local minimum alpha hat m will be close to some corresponding local minimum of the population log likelihood, and it will be pretty close given by certain terms. You can essentially think of this as some noise level, but the key point is that it also depends on this term d, which is, look at the ground truth joint density. This has a conditional independence graph, and you look at the maximum node degree of the conditional independence graph of your joint density, and it depends on that. Okay. Let me look at a corollary, because that was a I don't want to go into the details of that noise level. So if you focus again on our Sobolev order 2, and for the basis, I'm going to use a trigonometric basis, and again d is the maximum node degree of the conditional independence graph of my joint density, right? So again, if I assume that this d is small, that is still a non-parametric assumption, right? I'm not making any parametric assumption here. I'm just saying, given the joint density and its conditional independence graph, its maximum node degree is small. Actually, I'm not making an assumption explicitly that it be small. Our rate, again the mean integrated squared error, scales cubically with this in this maximum node degree, and it's n to the minus 4 by 5. Okay, so essentially the dependence on the dimension is now polynomial instead of exponential, and so that's what we have. Actually, it's logarithmic rather than even polynomial. Except that if you think this d scales with the dimension, then it will be polynomial. Okay, and so this is what we have. We have essentially a multivariate density estimation procedure that has a one-dimensional non-parametric rate, n to the minus 4 by 5 in this context, but you can also derive corollaries for other function spaces. Okay. And so here are some plots. So what we have here are, we are looking at some ROC plots for various exorcist densities. So on the top row, I have chain graphs where the underlying conditional independence graph of the density is a chain graph. So it's a simple Markovian assumption. And here it's a slightly more complicated grid graph where essentially there's a lot more dependency among the variables. And then each of the columns correspond to different densities. Okay, so this is just a very simple multivariate Gaussian, and these are slightly more complicated densities. And so here I'm comparing against GGM is just an estimator of a multivariate Gaussian. Non-paranormal is essentially a Gaussian copula, and Exorcist is our estimator that I just talked about with the truncated basis expansion. And so here what you can see is that when things are Gaussian, both the estimator of the multivariate Gaussian as well as the Gaussian copula do well, right? But when it's non-Gaussian, they essentially perform pretty badly, close to random, in estimating the. So these are the ROC plots. These are the ROC plots with respect to estimating the edges of the conditional independence graph. Okay, and so you can see that they don't perform that well, whereas our estimator is actually adaptive. So I don't actually tell it that it's cosine, exponential, or Gaussian. It's pretty adaptive to all these different settings under very, very sample-starved settings. And then we also looked at a whole bunch of real data. So here is one very simple real data. We looked at some financial data for some highly liquid future instruments. And so this is known to be not friendly to Gaussians. Right? So these are in particular multimodal, these are fat-tailed, heavy-tailed. And so we also don't have a lot of training examples. So if I use a Gaussian copula, so here all of these colors correspond to companies of a particular category, and so you would, again here I'm estimating the conditional independence graph of the joint density, and so you would expect that the conditional independence graph that you estimate has high dependencies among the companies in the same category and low dependencies across categories, and the Gaussian copula does not do that, but our Exorcist density does do that. Okay? So the high dependencies are all among companies within the same category, and so this is at least one qualitative way, but our results are all for the case what you may call the non-agnostic case, which is that when the true density is actually an Exorcist density, then our estimator works well, right? But we have no reason to believe that I guess these futures intraday data is actually follows an Exorcist density. But like I mentioned, the Exorcist density is makes, even though it seems stringent, an ANOVA type decomposition, is essentially all it's saying is that the conditional densities have exponential family form, which is actually not that stringent. Okay, and so that's that. So short talk. So we essentially looked at non-parametric density estimation, which is a big open problem that's attracted a lot of attention in the deep learning community these days, where most of the attention has been focusing on images, photorealistic images, but it's still a very important and open problem. And really, the key problem is the high sample complexity, right? And which is not that surprising, because if I don't make any assumptions, then a sample complexity that's exponential in the dimension is not that surprising. And so what we really need to do is to impose appropriate structural assumptions so that I can still do non-parametric density estimation. Again, by non-parametric, we really want to think very flexible classes of densities that fit real-world data, right? I don't want to say Gaussian, which is too parametric and too stringent. I want to look at flexible classes of densities, and this is one such category. And so here, the assumptions that it imposes, and again, we definitely do need to impose assumptions, right? In the absence of which this guy is high sample complexity is minimax optimal. So the two assumptions we impose is that the node conditional density has an exponential family form. And again, there are many results that show that even when a density does not have an exponential family form, it can be close to an exponential family form. Where there are these results for finite dimensional exponential families, and I think we can extend those to our settings. And the other non-parametric assumption is that the conditional independence graph of the joint density is sparse. And again, this is an assumption only in as much as our sample complexity scales polynomially with the sparsity. And we propose a computationally practical estimator, which again, its sample complexity is essentially corresponds to a one-dimensional non-parametric rate. Okay, thanks.
You assume the independence graph to be sparse, but do you need to know it in order to estimate?
No.
So you estimate the graph.
That's right.
In the procedure.
That's right.
And how is that done?
So we just compute the node conditional MME, and then so this is similar to even the parametric cases where you have a tuning parameter corresponding to. So you solve a regularized MLE. So here there is this tuning parameter lambda n. That larger it is, the sparser you will get. And the typical way to do this is some kind of generalized cross-validation.
I don't deny the interest of what you do from a modeling perspective, but sort of from a theoretical perspective, you look at convergence rates. I mean, all that matters is the complexity of the parameter space. So alternatively, I could say that the way, so I assume that my densities all have 2D derivatives for these dimension, and then you also always get the rate into minus 4/5. And so in what sense is this worse than what you do? I can also try to approximate all sorts of families in some sense from functions that have 2D derivatives, and I don't see how you could tell from a theoretical argument why what you do is any better.
Right.
And it would be computationally actually much easier. You do kernel density estimation.
Right. So actually, yeah. So that brings up, I think, a good point, which is, so ultimately, there are various ways in which you can bring down the sample complexity. There are various classes of structural assumptions I can impose. And so, for instance, I can even work with, for instance, a deep neural network that's invertible. And so that's my, I guess it's still a parametric family, and I can use that to estimate my density. So it all boils down to what are the classes of structural assumptions that are natural. And that in turn might vary depending on the type of data that you're looking at. And so one thing I wanted to argue was that here these assumptions are fairly natural and also very flexible. So for instance, the conditional independence graph is sparse. So this could be natural in settings where you don't really expect heavy dependencies, direct dependencies among a whole bunch of variables. This may not be the case in some other settings, but in some settings it might be true. So, and the other is that your conditional densities have exponential family form, which again seems kind of.
Again, from a modeling perspective, what you do is very nice. I'm just curious if there's any theoretical way to think about the improvement that you get from different sort of structures to approximate, by for instance, looking at the convergence rates of sort of some robustness analysis, for instance, when you look at perturbations from your model or something like that.
Yeah, so that would be an interesting, I think, desideratum for various structural assumptions, which is that, is it robust to departure from those assumptions? And so that's certainly an important thing. And so especially I think this is going to be robust because even when things are not exactly in exponential family form, they can be close, for instance. So, but that is certainly, so I don't think, one can make similar arguments, I think, even for finite dimensional parametric families, which is what parametric family should I actually pick? And I think more needs to be thought about that, yeah.
Just a comment that continues this discussion. I think we really need more comparisons about model classes. I mean, I understand you're in density, and so you try to generalize away from parametric class, but here the point is really different. I think you have a genuinely non-parametric problem, and there's a whole bunch of literature saying classical non-parametric estimation and econometrics where you have structural assumptions. I mean, I know a little bit more about regression, where you have additive models, where you have backfitting, where you have marginal integration, and all this stuff where you try to beat the curse of dimensionality. I think in density estimation, similar things exist. It would be very interesting to see how these classes relate to each other, right? I mean, I have the feeling, I have no problem with your exponential family, but I have a feeling that nevertheless, the conditional density, that when you condition on the others, that you have this structure, I mean, you have to do this for all of the nodes. It could be quite restrictive. It would be interesting to see actually how restrictive it is or not. I'm not talking about the approximation ability of the estimate. I think this is pretty good, but just to understand what is a robust or not so robust model, and then see what we can do with this. That would be very interesting.
So I guess two things. So the first thing is that, so again, so this is actually a paper out, I think, in NIPS, in NIPS. So we do actually talk a lot about the classical stuff that has gone on, and just as you pointed out, most of that stuff is in the regression setting rather than in the density estimation setting. But again, all of those actually can be ported just by making those assumptions in the logistic density transform, and I talked a little bit about that. But yeah, so that's certainly the case, and so this is still in that context. If you want to position it in that context, you can think of this as an ANOVA type decomposition with an additional restriction that there be that tensor factorization. So that's one thing which helps a lot. That makes all the difference. And the second thing is that with respect to the restrictive assumption that you pointed out, again, the assumption again is that each conditional density is an exponential family form. And so you said that, okay, so for one density that may not be restricted, but for all the densities it might be restricted together. But again, like I mentioned, the exponential family form, even if it's not the case, you can show that it's actually close to the exponential family form. And so it's actually, I don't think it's that restrictive, and we don't have any theorem of that nature, but I think it should be pretty simple because of some classical results.
If I understand it correctly, you're actually proving a kind of adaptive result because you're adaptive to the degree of the graph.
Right.
So, I mean, there's not much theory also in regression with high dimensions. You do the lasso, and then you do the linear model, which is also very restrictive. So in that, you're in that area, and then you go beyond that, right? Am I understanding it correctly?
Right.
So I think that's...
Right. And I should mention that going from regression to density estimation is very difficult because of the computational issues. Because imposing the assumptions in the logistic transform of the density, I then have this integral, multi-dimensional integral, that causes all kinds of havoc. And so that's an important thing.
So I think another very interesting, although it's quite personal bias, class of very related methods would be to work with shape constraints on the log transform. So if you have a log concave density, that's very much of your form. And if you also impose some sort of symmetry assumption, say in the simplest possible case, say spherical symmetry, then you can also get away from the cursor dimensionality. And you have a couple of properties that are very like yours. So conditionals of log concave densities are log concave, which is very nice. And you can also get down to a sort of very quick computation if you have these sort of symmetry constraints, and you can also study what happens under model misspecification. So I think that's another interesting...
Actually, so we have started to think a little bit about that, which is, so in many of these deep neural networks, even in the regression, but also in the density estimation context, one of the things that people like about them is that even without imposing, let's say, symmetry or various group invariances broadly, you still get that out if the data has those invariances. And so one question we have is that if you actually impose those and then do non-parametric regression or density estimation on those settings, what can you actually get away from the exponential sample complexity? So this is a question we are thinking about.
Just one last remark. So in multidimensional density estimation, there's a literature on trying to adapt to anisotropic smoothness. So you might have a situation where globally you have only a number of derivatives, but actually in one direction you're very, very smooth. And there are methods that are quite able to pick up this directional smoothness. And so then in a way, if you just are interested in sort of features that are parallel to a certain axis, you can also circumvent the curse of dimensionality. And I'm just curious if there's anything like that that could drop out of your construction.
Right. Yeah.
Dealing with anisotropic sort of regularity of the signal.
Right. Yeah, I think more broadly, I guess when you have low dimensional components and then everything else you don't care so deeply about. So I guess this kind of I guess I wouldn't call it semi-parametric necessarily, but it's a bit like the semi-parametric efficiency kind of a thing, where I care about these low-dimensional components and then just try to estimate those. Maybe that's another way to circumvent the curse of dimensionality, certainly.
Do you think your method would pick these things up? Or?
It might, but it may not be efficient with respect to that. Right.
I'm just curious, so don't you have to have tail assumptions on your function or on your densities because of the exponential transform? Doesn't it imply that you need to have on top of these Sobolev kind of assumptions on eta, some kind of also tail assumption?
Beta assumption?
Tail.
Tail assumption. On what? On the
Exponential theta.
So there are some conditions that we require, but as part of actually this theorem itself, that actually we most of the heavy lifting was actually done in the Montanari paper, which does have some tail assumptions. So I believe there are some. It has to look sub-Gaussian, I believe. I think sub-exponential also should be fine, but yeah.
But I think she's referring to something different, perhaps. The fact that eta e to the eta has to be integrable. But I think
To be integrable.
Well, you need to have a density.
right, because I
But that's
think
just bounded.
because he adds these C terms,
Right, right.
Yes, the single node
So
term
you
C
bound
that
everything by this measure
the C
behind it.
property
I was wondering why it came from.
are going.
So somehow the tail that you have are the same tail as the C that is the last term.
Yeah, yeah. So that was in the tails of the log likelihood itself, yeah, but not the.
Okay, I think we can stop this first part of the session. Let's thank Pradeep.